Hi, I'm Orpilla, and I'm going to present you a common source FET amplifier. So let's start designing the circuit. What we need, we have another capacitor here, another capacitor here, and we're gonna ground and the transistor. We're going to use and so let's start connecting them. And we go then start signing values. This works. This should be a easy signal. Sign 0 and start beat 10 mega ohm, be 1 mega ohm. Oh, sorry. Okay. Mm, 300. Lumen micro. Mm, let's start adding. Oh, I forgot. Let's take full scale for A9. So and connect to ground. Oh, then start adding labels. Just insert them. Okay, okay. Another one for Vout. Let's just rename this as RO. And CS should be RD. So our circuit is now done. So we are using a 10-channel JFET which has the terminals drain, letter D here, gate, and the source. So the source terminal is common between the input and the output, which is why we call it common source FET amplifier. We apply input to the gate terminal. We use voltage divider biasing made up of R1, R2, and Rs, which will bias the transistor in the active region and will work as an amplifier. Capacitor C1 couples the input to the gate terminal and capacitor C2 output couples the output. We are applying a DC voltage VDD, which is this 15 volts. Let me rename that for you. So we have here DC voltage VDD. So the transistor will take from the power supply VDD and will amplify the signal according to the nature of the input waveform. So we have here a capacitor CS, that capacitor CS, which is a bypass capacitor. It is connected across a resistor RS, which is this as resistor. So this is known as the source bypass capacitor, which bypasses the source current to the ground. So there would be less voltage drop across the resistor RS, increasing the voltage gain at the output. Whenever we do not apply any input signal, the operating current ID will flow through the transistor because of the voltage divider biasing. We apply signal to the gate, so this gate to source voltage is always reverse biased because of the voltage divider biasing. So during the positive half cycle of the input signal, the net VGS voltage decreases, thus the current ID flowing through RD increases. VGS and ID are inversely proportional, so when VGS decreases during the positive half cycle, current ID increases. The output voltage given as VDS is equals to VDD minus ID times RS plus RD, which we'll encounter later on in this video. So VDD is constant while ID increases, so we will get a decreasing voltage. Thus, during the positive half cycle of the signal, we will get the amplified negative half at the output. So during the negative half cycle of the input signal, VGS becomes more reverse biased. The channel width of the N-channel JFET decreases, which causes current ID to decrease. Going back to the equation, since current ID will decrease, output voltage VDS increase, which results to a positive output during the negative half cycle. So, field effect transistor are used in amplifier, analog switch, integrated circuits, and oscillators. So, advantages of JFET over BJT is that its impedance is higher than that of BJT. JFET are also easier to fabricate and more temperature stable compared to BJT. However, FET amplifiers exhibit poor frequency response due to high capacitance and exhibit poor linearity. So let us now determine the values that we need. So let's enter git.op and let's run the simulation. So here we have our values for the voltage across the gate, drain, and source, as well as the current along the gate, drain, and source also. So I have here prepared a document which presents the comparison between theoretical and simulation results. So let's first visit the equations to be used. So we have here the voltage divider bias formula. So we assume that Ig is equals to 0. The current across resistor 1 is equals to the current across resistor 2. VGS is equals to VG minus IDRS. VDS, VDD minus ID multiplied by RD plus RS. And VG is equals to R sub 2 VDD all over R sub 1 plus R sub 2. VD is equals to VDD minus IDRD. VS is equals to IDRS. So let's now proceed to comparison of theoretical and simulation results. So we have here the current across the gate is 0 amps. So if we try to look at the simulation, the current is equals to negative 5.20 picoamperes, which is approximately near zero. So let's look at the current across resistors R1 and R2. So we can see here that the current across resistor R1 and R2 are equal, which is equal to 1.36 microamperes. So let's solve for VGG, which is equal to R2 VDD all over R sub 1 plus R sub 2. So in entering the values, we have R2 as 1 mega ohm, R sub 1 10 mega ohm, and VDD 15. So this gives us 1.36 volts. So in the simulation, we also have 1.36 volts here. So let's go to VD. So VD is equals to VDD minus IDRD, which is equals to this with RD being 2000 2k ohms. So this gives us 7.63 volts. So at the simulation, this also gives us 7.63 volts is here. And Vs is equals to IDRS. So inputting the values with Rs equals to 300 ohms gives us 1.10 volts. So in the simulation, we also have 1.10 volts here. So let's now move on to VGS. So VGS is equals to VG minus IDRS. So we have here the equation, plugging into values, and we now have 0.26 volts. So in this simulation, we have to subtract VG minus VS, which also gives us the same values. For VDS, we have VDD minus ID multiplied by RD plus RS, which is equals to this. And when rounded off, we now have 6.52 volts. So when in the simulation, we have to subtract VD and VDS, which gives us also the same answer. So we now proceed to solving other values such as the output peak-to-peak voltage, the input peak-to-peak voltage, and the voltage. So first we type that run. 0, 10 and 0. Dot mesh. So we're going to use the dot mesh command that measures the output voltage, which is input voltage. So we have here the voltage gain, which is equal to the output peak-to-peak voltage all over input peak-to-peak voltage. So we have here the input current peak-to-peak, which is across resistor 1, output current peak-to-peak, which is across capacitor 2, the current gain, which is equal to the output current all over input current. Then we have the power gain, which is equal to the product of the voltage gain and current gain. We also have to measure the input power peak to peak, is product of the current along capacitor 1 and the voltage across V. And the output power peak to peak is equals to the current across capacitor I2 multiplied by the voltage plus V out. So these are all the commands that we need. Enter, just place it there, then we'll simulate circuit. So before moving on to the values that we need, let's first compare the waveforms of the input voltage and the output voltage. So as we can see, as I have said a while ago, during the positive half cycle of the input signal, we will have a amplified negative output voltage, and during the negative half cycle of the input signal, we now have an amplified positive output voltage. So let's now look at the values. So we now have here the output peak-to-peak voltage 7.87 volts, input peak-to-peak voltage 1 volt. So voltage gain, we have here, got something here, favorite param. So let's run here, and there we go. We now have the voltage gain at 7.87 volts. So we also have here the current gain and the power gain, which is 868.84 watts. We also have here the input power peak to peak and the output power peak to peak. So let's proceed to the measurement of the power bandwidth. So I have here the equation for the power bandwidth, which is the SR, or the slope, all over 2 pi output voltage peak to peak. So before we solve that, Let us first produce the waveform of the output power, which is equal to the output voltage multiplied by the current across the load resistor. So we have to place two cursors. So if we place here two cursors, this would give us the slope. So we're going to have to input this here and solve using a calculator. So 2.4711 over 257.87047 is equals to, here is that, 0.0488782795 or 47, no, 48.8988 milli. So that is the power bandwidth of our circuit. You can also look, so we can all, this is also the waveform for our power. Can be seen we have 681.29 microwatts. So that's it for this video. This is my common source FET amplifier circuit simulation. Thank you.